Let's come to, okay. All right, okay, so now we've fixed it. So now you can just talk. Oh, no, whoever is still remote, you can just talk. Like, if you want to talk, just unmute yourself, and then when you speak, everybody can hear from the speaker from the classroom, so everybody can hear. And I can use this Bluetooth device on my ear that when I talk. So now I guess, and I can walk away from it now because I don't need to be close to this. So I think the trick will be whoever wants to talk, I'm just gonna do this, and then that will be fine. Okay? Yeah. All right. Okay, so let's get started. Sorry about the missed minutes at the beginning. So few things before we start. I just want to talk a little bit about, let me see. Let me bring up the, okay. Okay, so what I want to do at the beginning is just to talk about a few feedback that I got. So last time, I guess I was playing with this all the time with like the stylus. I was playing with this and right next to the mic over here. So I think all of the recording has like a clicking sound at the end. But sorry about that. I think I will keep this away from me as much as I can. And okay, so I think that's, yeah, a few people actually brought that up. So I think it's important and remind me, like whoever is remote, when you zoom in, you hear some clicking sound, that might be me. So just tell me and then I will stop. And the other thing is for whoever is remotely joining in, please mute your mic. And you just unmute if you want to speak. And now with the system, I think we can all hear that you want to speak. So that should be fine. And also about the office hours of the interns, Bayan, I talked to him yesterday. He seems very excited about synchronizing his office hours as well. So what we're gonna do is he's gonna take my iPad, like this iPad, when he's holding office hours. So whoever wants to, so if you say, if you don't want to come, if you live in the TA, you think it's too far away, and if you don't want to come, we're still gonna have, say, so Bayan's office is gonna be, I don't know now, but we're gonna have, I think he's planning to have an hour and a half twice throughout the week. And once we know the hours, probably by the end of next week, we'll announce that. And then, but he will physically be in the math lounge with this iPad. But if you don't want to come over, you can also, so whoever, like Vassar students, you can also zoom in if you want. Everybody actually has an account. Yeah, and for remote students as well. So that means we're gonna have the office hours synchronized as well. And that actually brings up another thing I want to discuss about, like, what about my office hours? Should I also do that? Or like the remote students, you would prefer to schedule some separate appointment-based office hours separately? Or if you were like me to have my office hours, so I have office hours Monday for an hour, Tuesday for 2 hours. The thing is, I'm also teaching another class, so there might be other students like from a different class over there. So I think that's the only tricky situation. So you don't have to like, yeah, I mean, we all can think about it. And I will ask, I think, because some of the remote campuses haven't started their classes yet. So I will ask more once everybody's back on campus. But for now, I just want to put it out like as a choice, or like as an option, whether we want to do it synchronized as well. But anybody has any preferences or suggestions of what we can do?
I mean, as a remote student, I'd definitely be wanting just scheduling office hours. Like
appointment-based office hours?
Yeah.
Okay, okay. And
but I don't know if the other people feel the same.
Yeah. Yeah, I mean, I'm fine either way. I will definitely like get in touch once all of the campuses start school, and then probably I think that's next week after Labor Day. And here, I mean, I will just be physically there, so feel free. But just like Bayan's office hours, if in the end we all decide just we're gonna have synchronized version, you can also zoom in instead of like going to my small office upstairs. It's pretty crowded. Anyway, okay, so that's that. Thank you, Grant. Also, okay, so one of the things I want to talk about is I started like posting some discussion topics on Moodle. I know the remote students, you still don't have access. I'm sorry, we're still working on it. But overall, because in the end, you will have the sponsored accounts, and then you can have all those functions there. But just as a remark at the beginning, because I started posting something, and I think people definitely feel free to start a conversation and start a discussion and replying to others' comments. I think that would be nice. Okay. And one last thing I realized I can do, since we're doing this online component, maybe some flipped classroom style, will be I talked to Professor Josh DeLu. He is from the cognitive science department at Vassar, and he does a lot of Bayesian models and methods for cognitive modeling. So, and in particular, they like to do a lot of stuff with Bayesian hierarchical modeling. That's one of the topics that we're going to cover, I think, after fall break. So we talked about it, and he also likes the idea of, say, recording like a short video and then as an introduction of what they actually do as applications. So, so just another example of what we can do to create like multi-dimensional learning, I guess, is when we get there, we're going to start preparing the video. And when we get to the point when we are going to talk about Bayesian hierarchical modeling, I'm gonna ask everyone to watch like 5 to 10 minutes video just once or a couple of times, up to you. But I'm gonna post that videos made by Professor Deloy, and then we can, then I will use that as an introduction to what people can actually do with this kind of model. And then when we meet in the lecture, we're just gonna talk about the model directly. Okay, so I will give more information later, but I thought this will be something nice to share and mention at the moment, that this is something else that we can do if we want to save some time, and also just if people like to watch it at their own pace and multiple times, then you can have the option. Okay. All right. Okay. So so now let's get back to what we're talking about the other day. Okay. So so on this slide, I actually started a discussion on Moodle. I posted a few people's comments about the comparison between Bayesian and Frequentist, accomplished statisticians, and then they have some comments over there. You can disagree, you can agree, and I just want to see how people think about, especially if you have some experience with the Frequentist methods, if you see certain things good about it, not good about it, yeah, feel free to make comments over there. I think it's very open-ended, and I think it would be nice to see how people think, especially comparing at the beginning and maybe at the end or in the middle of this semester. All right, so let me just start with the toy example of actually how to do a Bayesian inference. So we started talking about last time that you will have a unknown quantity that you want to make inference about. Last time the example that I gave is if you have a coin, before you flip it, you're curious about the probability of getting ahead. So you don't know that probability, and that will be the unknown quantity that you want to make inference about. So in general, and even for the frequentist methods as well, we are interested in making inference for unknown quantity. So the goal here, again, is making inference. And the general procedure, we talked about that last time as well, but I want to actually just show them out all together here. For the Bayesian procedure, we really emphasize the prior probability. Later we're going to talk about distribution, but it's more about like probability that you yourself going to put for the hypothesis. So for the example that we saw before, it will be, before you see any data, what do you think, what's your guess, or like a range of guess that you think in the probability that you're going to get ahead. So that's before seeing the data, you're going to have a prior probability, and we actually write it over here. I write P parenthesis hypothesis. Because that hypothesis itself is pretty much just your prior, or your belief, or like the true probability of getting ahead in this case. And the second step is to collect data. In the example that we saw before, we just like do the flipping, and then each time, what the result is going to be data that you're going to collect. And the most important step over here now, it will be after collect the data, I want to update our probability of the hypothesis. In this case, it's going to be update what is the actual or better estimate of the probability of success after you have seen the data. So we call it posterior probability, and in particular, notice that here we write it in the conditional probability form over here. So it's P, hypothesis given data. We're trying to emphasize that you're updating this hypothesis, the probability of this hypothesis, given the data that you have seen. Okay, here, maybe just one last time, I talk about this frequentist p-value over here. Notice that the frequentist p-value, the one that we're more like familiar with at the moment, I think, is p probability data given hypothesis. So remember, anybody wants to just volunteer one more time about like interpretation of a p-value? If I give, okay, if I were doing I'm making an inference, I'm trying to make inference for an unknown quantity, and I get a p-value of 0.03. What does that mean? Okay, Eli, thank you.
That would be the probability that we could capture the observed data conditioned on the null hypothesis being true.
Okay, sounds good. Anybody else? P-value of 0.03. Any person remotely want to give a comment? Okay, so we write it down over here, probability of data given hypothesis. So if you get a p-value of 0.03, you're saying that given that the null hypothesis is true, the probability I'm gonna see my data, or a lot of times, the probability that I'm gonna see something as extreme as the data that I observe, gonna be the p-value. Okay, so it is really talking about the conditional probability that if the hypothesis, in particular, if the null hypothesis is true, what is the probability I will see something as extreme as my data? Okay, so see the difference between the p-value and then this posterior probability. And I want to emphasize here, like why a lot of times people think the posterior probability is more intuitive. Because you start with the hypothesis, you start with the probability for the hypothesis as your prior, and you get your data, and then conditioning on the data, you're gonna update your belief. On the contrary, the frequentist p-value will be, okay, I'm gonna assume my null hypothesis is true first, which actually I don't know if it's true or not. But p-value is really telling you that if the null hypothesis is true, what is the probability that you're gonna observe something as extreme as what you observe over there. All right, so let's just start with the toy example, and then I think you will know how this Bayesian methods is doing. I think maybe some of them have seen this type of analysis before. At Vassar, we talk about this in 141, in 341 as well. And this one is actually just an example that I have back when I was teaching 141. Okay, so for example is breast cancer screening. American Cancer Society estimates that about 1.7% of all women, American women, have breast cancer. Okay? And there's a foundation states that the mammograph can correctly identify about 78% of women who truly have breast cancer. And another thing is, back in 2003, there's an article suggests that up to 10%, let's just take it as 10% for now to simplify things, 10% of all mammograms are false positive. Okay? False positive meaning that you get a positive test, but you actually do not have, okay? You do not have breast cancer. So we're having this 3 percentages over here, okay? 1.7 of all women having breast cancer, 78%. So this 78% pretty much is if the woman actually have breast cancer, it's gonna identify it's true. Like you're gonna get a positive result. And then the last one is 10% of false positive. Okay. So now this is what you have as information. And now one woman is worried about like herself, so she went to clinic and then did this. The question is, for any woman, we don't know. Prior to any testing and any information exchange between the patient and the doctor, what probability should a doctor assign to a female patient having breast cancer? So this is a way to choose the prior. Earlier, we're talking about like in a very loose manner that, okay, anybody can have their own prior. You can decide whatever you think is right. But a lot of times we're actually trying to use something useful, something makes sense. So in this case, we're trying to use, say, established study or published study that what will be a good guess or an educated guess in this case, that I don't know anything about this woman, what will be the probability that she actually has breast cancer, and that will be my prior because I haven't done any tests yet. Anyone? Yes. 1.7%, right? Because we start with, because we know that from 2 slides before, we know that it's about 1.7% of all American women. So if we don't know anything about this women, we're gonna guess, a doctor gonna make an educated guess, that will be the probability. Okay, now the question becomes, when the patient goes through the screening, and then there are 2 competing claims here. Patient had cancer and patient does not have cancer. Now, if a mammogram yields a positive result, what is the probability that the patient has cancer? And I can rephrase it into a conditional probability here. What is the posterior probability of having cancer if the mammogram yields a positive result? Okay, so actually let me write it back. Did everybody try to write down the exact probability that we gave before? Let me actually put it out so we don't get confused. Sorry. Yeah, so we got a 78% at some point, and then also a okay. So what we know before is if the person has cancer. Give me a second. Okay. Okay. So what we had before is some probability is 78%. Okay, and that probability, if the person does have cancer, it's going to come out as positive. Okay, so that's what that 78% was about. So that's one thing we know. And the next thing we know is you can have 10% chance to have a false positive, right? So if I define so how can I do that as a conditional probability? False positive, what do you think? False positive, 10%. That is if you do not have the cancer, but the test is going to come out as positive. Right. So yeah, let me just use this notation over here. Okay. Okay. So this is what we have. Okay, 2 conditional probability here. And another thing we have, let me just write it over here, is we know that somebody has cancer. That's our prior. Is yeah, it's point, yeah. Oh, that's a bad decision, sorry. Because sorry about that. Let me just erase this. I was avoid writing that. Okay, yeah, this is what we know. And what we want to get, what is the posterior probability of having cancer if mammogram yields a positive result? So the question, if I phrase it into a conditional probability, that's bad decision again, sorry. Let me go over here. Give me a second. The question is, if someone comes out as positive, what is the probability that she has cancer? Okay. Okay. I will make sure that I do better writing next time. Yeah, sorry. But yeah, so okay, so we start with the prior probability that someone has cancer is 0.017, and we have 2 test results, like general test results. If someone has cancer, given that someone has cancer, it's going to come out correct as 78%. If someone does not have cancer, it's going to come out as positive as 10%. So the question is, if somebody has positive results, because that's what people actually want to know, right? If a woman comes out to be positive, she wanted to know that, given that I got a test positive, what is the actual probability that I'm going to have breast cancer? Okay. So what do you think we can do here?
We could use Bayes' rule.
Yeah. Okay. So how can we use Bayes' rule here?
The same thing plus 0.10 times 1 minus probability.
Okay. Can you say that again?
0.78 times the probability of cancer.
That's 0.17. Mm-hmm.
Divided by the same thing. Plus 0.1 times 0.983.
So what does that mean? What is each part about?
Probability that it's you with positive and breast cancer.
And here is positive and cancer as well. Mm-hmm. What about 0.1 times 0.983? Right? Mm-hmm. Does that make sense to everyone? Okay, so what we care about here is now we need to know, so think about the probability that we are trying to get. The question earlier is how to get the probability of, if I got someone come out as the positive test, what is the probability that the person has cancer? Okay, we're trying to do that conditional probability, right? Yeah, so on the top, sorry, yeah, the one that I just wrote over here, it's probability of cancer, having cancer, given that the test result is positive. Okay, so what does that mean? We know, so this is what we're going to review anyway, but I just want to remind you, for a conditional probability is, okay, for a conditional probability, okay, I got it. Question is, cancer given positive, right? And we know that it's two events, you have cancer or not, and then positive or not for your test. So conditional probability is the joint over the marginal, where the marginal is the condition that you're looking at, right? So if we simplify, that's what you're gonna do. And we keep the top the same for the moment, but in the bottom, if you're gonna come up with a positive test, there are two situations that can make it happen, right? You're gonna have positive and cancer. That's actually just on the top as well. But you can also have positive and no cancer, right? Yeah, so this is actually just conditional probability, and we are, even if you don't know about Bayes' rule, that's what you're gonna do, and then that's how it comes up to be, I think, positive and then having cancer over positive having cancer plus negative, oh sorry, positive, but you have no cancer. And that no cancer is 1 minus point. Okay? That makes sense? Okay. All right, if no question, I will go to this that I have. Yeah, so usually we use something like a tree diagram over here for simpler case like this, and you can actually draw it step by step. So you will see that for the first column over here, you list the hypothesis. So it's either you have cancer or no cancer, okay? And then the second column over here is about, given that you have cancer, you're gonna come up with positive. Given that you have cancer, you're gonna come up with negative. Over here, no cancer, positive, and no cancer, negative. Okay? And then you can just collect the numbers that you need. And in the end, you see that over here is what we just talked about, conditional probability, as the ratio of the joint over the marginal. Okay? All right, so what does that tell us? This particular point 12, what does that probability mean? We call it posterior probability of having cancer if you have a positive result, right? Oh, yeah, okay, yeah. So if this woman has a positive result, and then she actually increases the probability, right? Because at the beginning, the prior says that it's only 0.017, but now coming up with a positive result for the first time, say, she's gonna increase the probability. Like, we know that we're gonna have a higher guess because now she has a positive result. Okay, and now the probability actually like almost like 10 times than before. It's about 12%. All right, so you will see that this 12%, we call it posterior probability over here. But this posterior, if you think about it, so now this woman knows that she has 12% of chance having breast cancer because she has a positive result. Do you think 12% is high or low? High, low? Do you want to take another test just to make sure that you have it before you go through all of the treatment, right? So that's like, yeah, we're gonna go through that, like how to do the math, but then over here, I want to say that now we have this 12% as the posterior after the first test, right? But if I now go to the second test, I should incorporate this positive first test into my analysis, because now we know that this woman actually is different from any random woman out there, because she already has a positive first test result. Okay, so what that means will be that so we updated over here. That's what we're talking about. And then with the 12%, she's gonna go into the next step, right? If she's gonna take a next screening. And I want to emphasize here, this 12%, even though it's the posterior from test 1. If now I'm considering test 2, this 12% should be my prior. Because this woman is different from any regular woman. She has a positive test now. So if you look at it, if we're gonna do all of this calculation again, you will see that we should start with this 12%, because that's what we should update for, okay? So this is, we sometimes like to call it like sequential updating, because you get your, let me write it. You get your prior, and then you update. You update, when you update, you're really updating the probability of the hypothesis, even though we have different names for it. But for the first test, the prior is from just the regular, like about the whole population. And then once you get a positive result, you're gonna get a new probability about this case, and then that will be the posterior for the first test. But if you're gonna move to the second test, your old posterior are gonna become your new prior, okay? And this is sequential updating. And you notice that, so that's one feature, good feature, like appealing feature of Bayesian models or Bayesian methods is you can keep adding more data. You can keep updating your belief about the hypothesis as long as you get more data, okay? So if you can really, like say for more complicated models, if in your programming, if you can actually fit it in a way that they can automatically take into account of any new data you can take, and then keep doing this update, that will be pretty much you're just analyzing as more data comes in, okay? So let's go, just a really quick exercise over here. I actually already put the tree diagram over here. So you notice that now this cancer and no cancer, they change, right? They change from the posterior that I got. And then the data will still be the same in some way, because this will still be, because I'm just taking a second test, this will be if it's positive, if it's cancer positive, cancer negative, no cancer positive, and no cancer negative over here. So anyone for this case? So if the second mammogram also yield a positive result, I'm still trying to get probability of getting a second test positive and then cancer, right? So that will be so the true probability, like, because over here we get 1, 2, 3, 4, right? But we only really need to work with 2. We should work with this one and this one, right? Okay, so that, yeah, that will give us, let's see, point. Okay, and since like the first number is a little bit larger than the other number, so I guess between the choices over here, I'm gonna go with D, right? It's a little bit larger. I mean, you can use the calculator as well. But you see that now, if I have a second test to be positive, my probability of having cancer actually increases a lot, right? And that actually intuitively makes sense, because now I have 2 consecutive results, both yielded positive. So yeah, so people, I guess, like at this moment, you can choose to do a third test if you want, or if you decide to do the treatment, okay? So this is just a toy example. You see that you start with something, and then you start with the prior belief. Earlier, we were talking about anybody can have their own prior, but in reality, we try to use useful prior. In this case, the useful prior will be 1.7%, because that would just be the probability of having breast cancer for any woman in the United States. Okay? And then we're going to collect data. For this case, we collected 2 times of data, both of them positive for the results. And then after two steps of updating, we come to this probability of telling that this woman had this probability of 52% probability of having cancer. Okay, so of course you can keep doing more, or if you want to decide that you decide that yes, I should go through the treatment, then that will be it. Okay, all right. So really, yeah. So this toy example, just really quick over here. For Bayesian inference, you see the procedure. You start with the prior, you collect data, and then you update your belief, and then the belief is going to become a posterior. Okay, and the names are really just before data and after data. Before data is prior, after data is posterior. And then the good feature about this is naturally integrate data as you collect it, and you can update your priors. So your old posteriors is going to become your new priors. Okay? And also just in terms of interpretation, it's going to be easier to, especially comparing to the frequentist definition, it will be easier to interpret. And something I want to highlight over here is watch out, a good prior helps and bad prior hurts, but the prior matters less as the more data you have. Okay? So earlier we chose 1.7% because we know that's the population probability, and that should be an educated guess over here. But sometimes you might not have enough information to make educated guess. And the thing is, of course, we try to get useful prior information. Sometimes even if we try, we might not be able to get it. And that's the case where I talked about last time, that you want to put a really diffuse prior that I don't have very strong belief. So for this case, maybe if I don't know anything, I would put like a uniform between 0 and 1. That's just like extreme example over here. But overall, even if you had a bad prior, if you collect more and more data, the data are going to drive the analysis, because data are going to tell you more about the truth, if the truth exists. Okay, so, but of course, for our class, we actually gonna look through a list of different priors, data model, and then the posterior, and then we're gonna actually learn about how to choose prior over the other. Okay, because that's actually, I think, for Bayesian inference, it's actually like an art over there, because a lot of times, for computation reason, you might want to choose simpler prior, because that can work better. A lot of times, maybe it doesn't make sense. Or maybe it's, yeah, it doesn't make sense, then you should choose the one that you prefer or the one that you think really makes sense. But then that might be the problem of the computation, because then might not be, I mean, this is a toy example, so it's very easy, but in a lot of analysis, it might not be. Then it's actually like a trade-off between these two, and then you have to both increase your computation skills so you can do better in terms of what kind of prior that I want to use. I can still make a program out of it. So that will be something that we're gonna keep exploring. Okay, so another, like philosophically, these are the biggest, I think, biggest difference between frequentist and Bayesian. So no matter which approach that you take, they try to use the data to learn about the unknown parameter. So we use theta as a generic, like generic representation of the parameter, and y, capital Y is just the data. Okay, so for the frequentist, let's look at the left-hand side first. For the frequentist, we, like, people believe that data are repeated samples, okay? And that's actually a very strong assumption, and that's the base of how all of those like linear regression or even ANOVA, etc., all of those methodology is based on this very strong assumption that data are repeated samples. And I highlight over here in red, in frequentist methods, they treat parameters fixed. They think the parameters are fixed, and what I see in the data is just a random sample given that parameter. Okay? However, if you look at the right-hand side for the Bayesian, we do it in the other way. We assume that data are observed from a realized sample, and then the data actually fixed, because that's the only thing that I have. And I want to make, I actually assume that the parameter is random, and then I'm going to try to make inference, given that I observe this set of data, what will be my posterior, for example, over here. So this is the form that you see before. So this is the data, and this is the parameter. Yeah. So we're going to see that more later as well. But in short, I want to actually just talk a little bit about here. That's the usual way that we write about the prior. And then you can still write this, but this will be the data. And then combining this, we're trying to get the posterior. Okay. Yeah. So this is the steps that I was talking about, like the procedure. You start with prior, and then you collect data. You may do multiple times of collecting data, just like what we did for the toy example. And then in the end, you're trying to get the posterior. Okay, so we'll see this representation, like notation, very often in the future. And I think on this slide is also like useful to point it out how they look. Okay. All right. So earlier, so pretty much this is the data part. Sometimes we talk about it as model. Okay. So this is just an example, extending to statistical analysis that you might have heard before. Theta is the unknown parameter. Okay. And then say, for example, if I want to do analysis, I want to make inference about the success probability. And if I'm doing flipping a coin, then that will be a binomial distribution, right? So the data will be a binomial distribution. And what I want to know is this P is the success probability. So here, my theta will be P. Okay? Yeah. And then over here, model for the data, that's this part that I talked about before. And then in this case, if we're doing success probability of getting ahead, then it's a binomial of n trials P success probability. Okay, yeah, and Y can be Y needs to be the number of success out of n trials. Okay? So if we put back into the context that we talked about before, if you are flipping a coin for 3 times, and I define P to be head, getting the probability of head, and then the example that we gave before will be Y is 0, right? Yeah, oh, sorry. Let me just remind you what we talked about last time, the toy example as well. Like you flip a coin for 3 times and you get 3 times tails, but our interest is the probability of getting a head. So for that particular data model, it's gonna be n equals to 3, Y is the number of success is 0, okay? But still, this hold because it's a binomial distribution based on the assumption that we have, flipping a coin. Okay. All right. Okay, so this is the general prior distribution probability. We talked about this sampling model. This is the data. Posterior is doing through this update. So you see that this now, like this form is much more formal in a sense, or more complete. So on the top, so we're still interested in, given the data, what we're gonna do about the parameter, okay? We want to update the belief about the parameter, given the data. So the first part over here, you will see that it's just the application of conditional probability. Conditional theta given Y will be the conditional, so on the top is actually Y and theta, but you can also rewrite it into a different form of the conditional distribution. Okay? So let me write over here maybe. Theta and Y. Okay, so this is the prior. This is the data. Okay. Yeah. And here down, this is the marginal probability of data. Okay. Yeah. Make sense? Yeah, so if you break down this Bayes, so this, the first part is the Bayes theorem, and if you break it down, that's how it looks like. So we want to get a conditional probability over here, theta given Y, and we know that conditional probability theta given Y is the joint of theta and Y over probability of Y, but then theta and Y can also be written in the different form of conditional and marginal. Okay, so what this is about, let me write over here, is if you think about Y and theta, the joint distribution of the parameter and the data, you can either do prior times the data, or data times the probability or distribution of theta given Y. So this is actually 2 ways of representing this joint distribution that we're trying to use in order to use the Bayes theorem. So what we know is, we know, let's see, we know this. And we try to, this is the unknown, because this is the posterior that we're trying to figure out. So we're pretty much reusing the joint as the product, the marginal, and the conditional. We're reusing it twice in order to get the Bayes theorem work. Okay. And then over here, this is just generic, because if you look at down here for the Y, the marginal of Y, the marginal of Y will be all kinds of theta that I can take, and I integrate out theta. Okay. So in the breast cancer case down here, it was a sum, because we only have 2 outcomes, and you sum them up. Okay, so for discrete case, you're gonna replace the integral with sum, And if it's continuous case, we just generically using this integral. Okay, but you see that later, because if you look at, because in Bayesian methods, we're going to assume that the data is fixed. Okay, so we're going to try to ignore what is in the bottom and only care about the top. Because if you assume that the data is fixed, the PY is going to be the same. You just don't know what it is, but it's going to be fixed. So I'm going to try to ignore that in terms of my analysis. But if you want to write it out formally, that's what it is. Okay? So later you will see that instead of writing an equation, we see more and more of this approximation. Oh, sorry, proportion. I'm sorry, proportional. Yeah. We use this proportion sign to get rid of worry about how to do this margin of y. Okay? Yeah. Let me just write that out really quick again. Okay. Yeah, this is what we start with. And we know that the joint of theta and y can be written as the prior multiplies with the data, and then divided by y. Okay. And here, we know that the Bayesian methods assume that the data is fixed. So the margin of the data are going to be fixed. We just don't know what it is. So in order to simplify, we actually care mostly only about the prior and the data part. So that's what you will see mostly in this class, because as long as we assume that the data is fixed, it's just a normalizing constant over there to make sure that it's still a proper distribution. But this is what we work on. So this is proportional too. Make sense? Yeah. Okay. All right. So let me do this. Okay, so let me just demonstrate. I'm not like just making things up, and then let's try to think about, okay, the question that I thought would be interesting is, what if we want to make an inference about the percentage, let's say P, of all Vassar students stayed up at least one night last academic year to get schoolwork done? Let's say that's the goal. We're trying to estimate a probability of how many, like percentage of people are actually gonna do that. And suppose we only have a sample of 10 our students, like in this classroom. So that will be our data. And we're gonna ask whether they stay up at least one night last academic year or not. So let me just write it out over here. How many we have today? Let me just do, if you guys don't mind, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so the 10 people over here, did you put out stay up at least one night last year? If you do, just raise your hand. One? That's fine. no, that's fine. Okay, so one. Okay, so let me write it down over here. So the data that we get is 1. Okay, and the sample size that we're gonna have is 10. Okay. Okay, and I'm just gonna make some assumption over here that we're gonna just make, it's actually incorrect, but let's just try to make the assumption here that the sample is representative of Vassar students at large. And it's just an illustration of idea. And we actually, so based on this data, we're gonna try to build a prior distribution and use Bayesian inference to learn about this P. Okay, so let's get it straight here. We have the data. The data tells us that out of 10 Vassar students, hopefully representative, we have 1 student stay up all night last semester, or last academic year. Okay, so this is the data. Okay, maybe I should have done this, like get the data afterwards, but okay, so suppose now we have the data now, like the percentage, like you can see it's like 10%, right? But assume, sorry about this, like the proper weight is, we haven't seen this yet. Like before you see, like actually out of 10 people, like in this classroom, only one had done that. But yeah, before you see that, just based on a guess, let's say, what would be your guess of this probability P from 0 to 10? And let me just simplify it so we don't have like numbers all over the place. I'm just giving you, let's see, 11 choices here. Okay, so I just want to ask everyone to guess just your prior belief, because now I'm trying to demonstrate one way to create a prior as a whole class. You understand what I'm trying to say? Okay. We have the data already, which we shouldn't have, like I should have counted like after. But the goal is now as a whole class, let's try to come up with a prior distribution. It's simplified, it's a discrete distribution. You only have 11 choices, okay? And you just choose one of them. And then I'm gonna count how many choose, like how many choose 0, how many choose 0.1, etc. And then I'm gonna create, like construct a prior distribution like this, and then demonstrate how that can be done, like how this can be combined together with the 1 out of 10 data set, like data point that we have to do a Bayesian analysis. Okay, and I think, let's see, we see Grant, Julia, and Shirley as well. If you guys want to just make guess about Vassar students, that's great. And we can, yeah, let's just raise, yeah, I'm just gonna ask, like, raise up your hand as what is the choice that you're gonna make. So let me count how many we have. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 17 here. And okay, if you guys don't mind, just become part of it. We're gonna have 20 people in total. That's a nice number. So everybody just choose one, and I'm gonna construct a prior from us to see how a Bayesian methods can be done. So we're not talking about how the data is collected. I mean, it might not be representative, it might not be a good data set to work with, and the prior is very, like, very crude as well. I'm just using us as a way to construct it with the prior. You might have some better guesses out there as well, but let's just use this as a way to demonstrate how things is done. So let's do, okay, out of 20, how many people think is 0? 1? Oh, not 1, sorry, 0.1, 10%? Just raise up your hand a little bit more. Okay, so we got 4 here, 4 here. What about you 3? Okay, so when I count, like when I get to that number, you can just unmute and just say, okay? Yeah, okay, sounds good, thank you. So we got 0 and 4. Okay, what about, huh? Oh, so, Grant, did you raise your hand?
Yeah, we have a raise hand button.
Oh,
I don't know.
I didn't know that. Okay, yeah, but maybe like just unmute yourself. But I guess I have like 17 pairs of eyes here to look at you. So okay.
Sure, yeah.
So, okay, so you chose 10% as well?
Sure, yeah.
Okay, sorry. So let me erase that. And then, okay, all right, 20%.
I do.
You do? Okay, so 1 for Julia, 1, 2, 3, 4, 5, 6. Okay, 6. Okay. 30%. Ooh. 1, 2, 3, 4, 5. Okay. And Shirley, please just shout out if you want. So we got 5 over here. Okay. 40%. 2. Okay. Are we getting? Oh, okay. We're still not. Oh, sorry. Shirley said point. Oh, you said 0.6. Okay, 0.6 over here. Now let's see how many we have here. No, I have one more person haven't made the choice yet. Is that Shirley? Okay, I think she's okay. But everybody made their choices here. Okay, all right. So I'm not sure if she's gonna respond. So, oh, okay. Wait, can you guys? No, we can't. I said okay. Thank you. So we got. Sorry about that. You have to unmute yourself when you speak. So that's right. Right. That's Huh? Oh, okay. But can we figure that out later? Let's see. sorry, I'm trying to like multitask. This is hard. Oh, okay, so that's right? We have 11. Yeah, we got 20 over here. Okay, so this is the prior that we have. And this is, so prior over here. And this is the data. Okay, make sense? Okay, now let me show you how to use, so I wrote a R function beforehand to do this. So I'm just gonna put out my program and then raise everything over here. Give me a second. Let me put this out first and then let me record those numbers so I don't miss things. And then I'm gonna switch the view to my laptop so you can see. Okay, so we got 0 for 0, and then 5 for 10%, 6 for 20, 6 for 30, 2 for 20, 2 for 40, 0, and then 60%, 10%, 9, 10. Okay, all right. Now I have everything. I'm going to show you the code that I did. Okay. Sorry about that. Oh, okay. Hey, let me see. How can I do this? Oh, okay. Let me share screen here. Okay. Sorry, because I wasn't sure if I unshare this, all the numbers gonna be gone. So I wanted to record it before I can show you my laptop. But it's better if I can actually show you how I was importing those numbers. Anyway, okay. So everybody can see this? Okay. Yeah. So this is just I shared this on Moodle and as well as sent it to all of the remote students as well. So this is the prior. Okay. So it's just a short script in R that I was trying to use to demonstrate this. You can explore and play with this later, but let me just show you how it works. And then for those of you never seen like R before, this might be a good way to look at it. So I create a vectors of 11 numbers and just recording the prior values from 0 to 1 with 10% increment. Over here, I assign the prior probability that we just get from everyone. Okay, so over here, let's just double count. So 5 for 10%, 6, 26, 30, 2 for 40, and then there's 1 for 60. Okay, and just now, the data is different from what I wrote over here. It's N is total, is the number of people that we collect the data from, and we only get 1 success, because out of this 10 people, they say there's only 1 person did that. So this will be the prior. Oh, sorry, this will be the data. And I will just skip all of this for now, but I just want to show you how a program can actually be used to compute the posterior based on this. Okay? So now I computed everything, and let me show you. Can you see this? Yeah, so I create a vector recording all of the prior values as a column, prior probability as a column, and posterior as a column. Okay, it's not a great way to show how my posterior changed from the prior, right? Because even you can see like a little bit, but like you can see like number 2 over here. Yeah, got increased because that's kind of like 10% got increased because that's very close to the data point that we get, right? Yeah. Anyway, so this is it's a pre-written function to show you how that can be done. But let me just plot it for you as well, because I think that might do a better job in terms of telling you how things are changed. Let me move because all of the screens are here. What is this? I'm sorry. Can I? Oh, I can close everybody. No, I cannot. Sorry. Give me a second. Just gonna. Oh yeah. Okay. Sorry about that. Okay, so you see this this particular plot on the right over here. So we have 10 different prior values and 10 different posterior values as well over here. We're just treating as discrete. And then over here, you see that the prior that we have, which is the red dot over here, is representing what the what all of us thought about the prior distribution of this probability, okay? And it's discrete. And you see that the posterior after the data, okay, I guess I should have also plot the data over here because the data is a spike over here at the 10%, right? Yeah, over here. So you see that combining, and then all of the cross, the blue cross, are the posterior probability of each of the probability values over here. So you see that the data drag the posterior a little bit closer to that 10%. Okay, so this is, it's not something like very complicated, but it's just one way you can do like a very simple Bayesian inference over here. And I share this code with you all, but I really want to emphasize like just the whole procedure. What I should have done just now is actually first ask you about your prior belief before actually I count that 1 out of 10 is actually have done that before. So we can come up with the prior and then collect the data and then having certain functions. So in this case, you need to write a certain function to do it, to compute all of the probability. But really, this function is just doing the Bayes rule. But now instead of 2 outcomes, I'm going to have 11 different outcomes over here, and I'm counting all of the cases. Okay, so that's what this R code has done for you. But overall, I think I want to use this example of how you collect the data, how you come up with prior, how you can compute it, and in the end also show it. I don't think I've done a great job here in terms of showing how the update is done, because I should have also added a data point to show how the data is actually dragging the posterior distribution close to what it is at the moment. Okay, but I will update this and then update on Moodle and then with all of the code as well. So this is a demonstration, and I share this with you all, so you will be able to play with it. You might want to like check with another group of friends to see what they think, and then yeah. But overall, this is a very straightforward application of Bayes' rule and how Bayesian inference can be done. Okay. All right. So that means I can do. Sorry about the back and forth. Okay. All right. Yeah. So yeah, before we're going to end today, I'm just going to talk a little bit about the different analysis goals that Bayesian methods can do. So it's definitely going to go beyond just updating the prior distribution to obtain a posterior distribution, because this kind of procedure is just trying to get us making better inference once you get the data about the hypothesis. But people definitely want to do other things. For example, if they want to do predictions, because even in the frequentist method, you want to do predictions for future events or future situations. And then in Bayesian methods, the prediction is actually done in a very nicely easy way. We're going to get to that later, because we will be able to get something called, so here. Yeah, we're going to learn about, so remember what we had before is the posterior is going to be a combination of the data and the prior, right? Yeah. And then think about, so if you try to make prediction, say Y star is the prediction that I want to make, okay? And then I'm making the prediction based on what I observe, right? Yeah, we're trying to get rid of the parameter in this case at the moment. Okay? So if you think about this, what you can do, this is just a review as well. For example, if I have the product of these two, what that gets me. Sorry, maybe let me write it in a different way so it's easier to understand. Sorry about that. So if I can get this, and if I just integrate out theta, I'll be able to get the predictive distribution, right? So if I have the joint distribution of a prediction and the parameter given the data I get, and then I integrate out the theta, I should have the marginal. Now it's still conditional, but it's the conditional of y star given y only, and that's my goal, right? So what I just did over there is you can break this oops, sorry. Make sense? Because what this is the posterior that we're gonna have. Okay? Yeah. So this is a way, like, I mean, from the probability point of view, how you are able to get prediction. Because now you have, based on what we do with the posterior, we have all of them over here. And then we can make prediction. Because then this is just like part of like what I was trying to go over anyway, is how you can get this marginal, this conditional, I mean, by integrating out the theta. Because theta is just the parameter in the model. Okay? And this application, I mean, this few lines is review itself, but that's really the core of how you can get prediction. Okay? And when we get there, we're going to talk more about it, of course. But here, I think it's a nice preview of how things can be done. And also, of course, test of hypothesis you'll be able to do. And now the interpretation of hypothesis will be much more intuitive, because it will just be the probability. Say if you have a confidence interval or a credible interval, then it will just be the probability of 95% that your parameter is going to be in that interval. Because now you're assuming that everything, like all of the parameters are random in the Bayesian methods, and making decisions, that's actually a different field within the Bayesian methods. But I just want to say it out loud right now, these are all of the ways that you can do beyond just simply like updating the prior, updating to a posterior, et cetera, et cetera. Okay? All right, I think we're gonna end here because we're running out of time. And oh, we got a question. But you guys can pack, that's fine. You see, after your prior, oh, you cannot see it, right? Oh, only I can see it. Huh, okay. Okay, Shirley, I got your question, but somehow I'm the only one who can see it on my iPad. So I get back to you because everybody's leaving here, but I'll get back to you and I post these questions onto the Moodle and then you can all see it as well. Okay, yeah, so Shirley, I will get back to you later, I guess, not now, but okay. Cool, so I post the homework is due not next Monday, but the Monday after. Okay, and I think most of it is some probability stuff. We're gonna do the review of that a little bit on Wednesday as well, and then we're gonna continue the actual analysis with one parameter model. Okay, all right, thank you. Oh yeah. Mm-hmm. Good. What do you mean? Oh, the homework? Oh, okay. I think a few. Thank you. I think, let me think the questions. Yeah, maybe let me put it out over here so I can give you a better suggestions. Where did that happen? Yeah, so I think 1 and 2, and mostly 3, maybe 1 and 2 definitely you can do it because that's applications of the Bayes rule that we just talked about, but in a different situation, like in a different context of like computing conditional probability, etc. So I would recommend you can start 1 and 2. You can probably finish it. Yeah. All right.
So I understand that the prior affects the posterior, but like, what are the actual calculations, or is that just something we do in R?
So for today's demonstration is only in R. Yeah, but starting on Wednesday, after we review a little bit of the probability theory, you can actually see how that is done. In the we have you can like play with it to see, yeah, because that's just, yeah, it's doing the Bayes rule, like the stuff that I show you before. Can I? Oh, I don't know. I don't want to like close this because she has a question. Yeah, but remember what we have seen, like probability of theta given y will be probability of y given theta times probability of theta, and then divided by like a sum or an integral over there. So the function that I wrote is doing the sum for all of the 11 different situations. Yeah, so for that particular case, it's discrete, and you'll be able to get the prior and the likelihood for all of the cases, the data for all of the cases. So I will be able to do it. Yeah, but good point. Maybe I will. Yeah, I think on Wednesday I will mention that as well. Yeah, yeah.
Also, so the prior, like, it makes sense that so we give an inference that I don't really base off anything. I just guess.
Yeah. So that's the thing. So people want to make good guesses, right? You want to use good guesses. So we're gonna learn more about because this, all of the examples that we have talked about is more like toy examples. Like, okay, yeah, like what's the probability of success, for example? Yeah. But later you will see that depends on different types of the data model. Like say in this case, what we just did is actually a binomial. Yeah, and then there will be some nicely written down ones for this kind of data model. But then if your data model is normal, for example, then there might be something out there. There are things out there that you can make better use of the prior. Yeah, so because later. Yeah, right. So you're right. So it's actually a lot of discussion out there because sometimes people say, okay, yeah, even though you're saying that you get this prior based on your belief, but it's really based on some data already, right? Yeah, so there are discussions about whether you're like reusing the data multiple times, is that appropriate, is that legitimate, et cetera, et cetera. Yeah, but I think what we have seen so far still mostly is still about just point estimate, like one particular point. But later, once we start on Wednesday, you will see that we're actually going to move to distribution. Yeah, and then from the distribution point of view, you can incorporate uncertainty. Like if I put a uniform distribution, even though it's from 0 to 1, but like they have a variance as well. Maybe for a probability I put from 0 to 1, the variance is large, right? If I think, okay, it's going to be about 0.5, I think it's not going to be far away from that. So I can put 0.4 to 0.6. A uniform over there, right? So so once we move to distribution, I think you will see a better picture of how things are done. But I think you're right, because now there are things about whether you're reusing the data multiple times, et cetera, et cetera. I think there are issues. Okay. Yeah. Great. Thank you. Yeah. Oh yeah. Oh yeah. Oh yeah. So Y star is a prediction. Yeah, it's a new prediction. Yeah. So Y is the actual data, theta is the parameter, and Y star is something we say okay, I have 10 days of data. Now I want to do the 11th day. So I just use Y star to represent it. Yeah, exactly. Thank you. Yes.
So actually, I use the same iPad
to
take notes.
Okay. Suggestions, right?
Yeah,
yes.
Just one thing that I noticed is, and this is something that I did at first when I was using it, it's the temptation is to hover your hand, instead of pressing your palm against the glass. But actually, if you press your palm against the glass, it will still detect.
Yeah, I think. I think I did it, but I still look very shaky, I guess.
Right. So, and also the other thing, if this isn't, I don't personally care. This is just stuff that I learned.
Yeah, of course. Yeah.
I also found that like having it be like entirely flat, so like folding the case like totally.
Yeah. So you say that like if I do, what does that mean? If I put this out like this.
Or I was thinking like so.
Oh, sorry. Yeah. Go ahead.
Even I was thinking even just like. Yours doesn't fold that way.
I don't. Yeah, but maybe that means I should get a different. Yeah. But so you think if it's total flat, it's easier to write with?
It's a little bit for me also.
Okay.
Just getting used to.
Yeah.
Like writing on it.
Okay.
Like, at this point, it's actually neater for me than writing on it.
Yeah. Oh, nice.
The surface is different.
Okay. Yeah. Let's talk. Yeah. I mean, I'm happy to learn more skills, to be honest, because I noticed that just now, like Zoom has good functions of like I can get a whiteboard out and I can just write on the whiteboard, but I still think like one way I can do it is to do more, I guess, more of like more space in each slide so I can like write better. Or they're just things like even to switch between, and I was worried about like the data gonna be gone, so I was doing it. Yeah. But
it's really cool. Like devices help me a lot.
Okay. Good to know. Good to know. Okay.
It was a weird adjustment.
Okay.
Like a couple minutes.
Okay. So I've done my first week, so hopefully next week I'll be better.
Also,
Okay. Thank you. Yeah. I'm still. Yeah. To be honest, I'm still like very nervous. I feel like I could be much faster if I'm teaching in the regular classroom. To be honest, and I think certain things like slow down, and then I don't know. Yeah. So it's also
I think it's an adjustment.
Yeah.
It's different. Like I'm not used to that process of PowerPoint. I think it. I don't know. I think we'll.
Okay. Sounds good.
More sustainable.
Thank you. Bye-bye. Yeah, in the future, yeah. So hopefully I don't like get like burnout, and everybody can be convinced that you won't get burnout, and then people will be willing to do it.
It's work to adjust the with that, but I think it's worth putting in. Like,
Okay.
For example, we'll see as the course goes on, but I'm really interested in the possibility of doing some sort of like advanced spacing. I was going to take Professor Morin's because that's not really relevant to the kind of work that I'm interested in.
Yeah.
And that's the kind of class that would be very much facilitated by some sort of like online.
Yeah. Sounds good. Thank you, Eli. Yeah. Have a good day.